So we're going to break this problem up into two separate parts. The first part is figuring out the elongation due to tension compression, and then we're going to separately, the second part, figure out the elongation due to the temperature change. Well, it's actually going to be a contraction in this case. And then we're going to add up those two deltas to give us the total, and the total has to be equal to 0 because it has to, those walls are fixed. And that's going to give us the extra equations we have. So the first thing we need to do is figure out if maybe this is statically determinate. We don't have to do any of that. It's not. Okay, so free body diagram. We have a force RA. Everything's horizontal, so that's all I'm going to do. These are fixed joints, so really it can provide a full vector of forces and a couple. We're just not going to need those. And then RB. And then a horizontal force of 10,000. And the x component of Newton's second law says RA plus RB minus 10,000 is equal to 0. So our first useful equation, and the only useful equation we get from the statics, is RA plus RB is equal to 10,000. That's one equation for two unknowns, so we need another equation. So we need an equation, and the equation is going to come from saying that the total elongation is equal to 0, where that total elongation is equal to the elongation due to tension or compression and the elongation due to the temperature change. Okay, so I'm going to start with the one due to tension compression. So here's what we know. We know that there's a force here of 10,000 newtons, a force here that we've already named RA, and a force here that we've named RB. And in order to calculate the elongation, we need to find the internal tensions over these two sections. So we're going to have to do cuts. So cut 1 is valid for x's between 0, so all the way at the left, to 0.5. So we have an RA there, no matter what x we choose. We haven't gotten to the 10,000 yet, so the only other thing we have is a T here, and we also, in general, we would have the shear force and the bending moment, but those are going to be 0 here. Newton's second law, x component says RA plus T is equal to 0, so T is equal to negative RA. Okay, so that's the relationship between the internal tension and the external force RA for the whole fatter part, the whole bigger cross-section. And then for cut 2, for x values between 0.5 and 0.75, We still have RA. Now we also have the 10,000, but we're never including the RB because we're always cutting it short of that. So the only other force is that internal tension. And Newton's second law, X component says RA minus 10,000 plus T is equal to 0. And so T is equal to 10,000 minus RA. So those are our two expressions for the internal tension. And now we can use those to calculate the elongations. For the first piece, the elongation is, so the formula we're using says TL over EA. So we have negative RA times L of 0.5 divided by E, 100 times 10 to the 9. And then A was at 0.01. And so you get 0.5 divided, so times 10 to the minus 7, 5 times 10 to the minus, oh yeah, the 100, negative 10. All right. And then the elongation for the second part, our T is the quantity 10,000 minus RA. The length is 0.25. The Young's modulus is 100 times 10 to the minus 9. And the cross-sectional area, what did I say there, 0.003? And what do you get for that?
The whole thing should be minus 8.33 times 10 to the negative 10 RB plus 8 times 10 to the negative 6. Oh yeah, RA.
Okay.
Your RA
Can someone just tell me what this is so I can...
8.3 repeating e to the negative 6 minus 8.3 repeating e to the negative 10 RA.
Okay.
which I just did.
That's what you just told me?
Yeah.
I thought you told me the whole answer.
No, that was the whole thing for that.
Okay. So the total elongation due to tension is negative 5 times 10 to the minus 10 RA plus 8.3 times 10 to the minus 6 minus 8.3 times 10 to the minus 10 RA. And so that's 8.3 repeating times 10 to the minus 6 minus 13.3 repeating times 10 to the minus 10 RA.
You can't put that equal to 0.
Not yet, because the total elongation is the sum of the elongation due to the forces plus the elongation due to the temperature change. So we have to add them all together. And now the temperature change. The elongation is equal to the coefficient of thermal expansion times the length, and for this one we can include the whole length, times the change in temperature. This time the temperature dropped 150. So this will be negative 150. And what do you get for that?
Negative 1.125 under the -3.
Okay. So now we have the two pieces. And so the total elongation is 8.3 repeating times 10 to the minus 6 minus 13.3 repeating times 10 to the minus 10 RA minus 1.125 times 10 to the minus third, and all of that has to add up to be equal to 0. So 13.3 times 10 to the minus 10th RA is equal to 8.3 repeating times 10 to the minus 6 minus 1.125 times 10 to the minus third. And that basically just comes out to 1, 2, 3. That doesn't even show up. The 1 times 10 to the minus 6 I don't think even shows up to the significant figures I have. So what do you get here?
Negative 8.375 times 10 to the 5th newtons.
Times 10 to the 5th newtons.
Wouldn't it be the 1.125 would dominate, right?
Yeah. And that's the negative 1.
Isn't that 8.3 a negative 8.3?
It is negative right there.
I moved the negative 13 over to the other side of the equation. So that's positive, and then we have this one positive and this one negative. Looks right to me.
I think we're just confusing ourselves right now.
Yeah. Okay, so that's RA. So how do we find RB? Yeah, just plug it back into that first equation. This is the second equation. And what do you get for RB?
8.475
And so
No?
RA plus RBS equal to 10,000.
right, times 10 to the 5th, so 10,000 is 10 to the 4th, so I think that's right. And so we get, so this member is pulling out on both sides of the wall. Okay, it shrunk a lot because of the temperature change, and that was enough to make it pull in on both sides of the wall. The wall's pushing on the two, no, the wall's pulling out on the two ends. Any questions about that? Jared? No? Okay. All right, so the next thing is very similar to this, angle of twist. Angle of twist, and statically indeterminate bars in torsion. And we're going to be doing this for circular cross sections. You could use a very similar analysis for thin-walled tubes, and you could probably figure out how to do it based on the way that we're doing this, but we're just not going to go into it. Okay, so what we're talking about is if you have a bar like this and you apply a torque to it at the two ends like that, say that you start out with a line like this, okay? After you apply that torque, that line is going to do this. And this angle phi is the angle of twist. Okay? And the angle of twist is going to be given in radians. For elongation due to tension, we had three equations. We had one for all constant values, delta equal to TL over EA. Then we had one for piecewise constant values. The sum formula said delta was equal to the sum of TI, LI over EI, AI. And then we had the continuous one that was the integral formula over the whole length of T, L over E, A. And so it's going to be similar with this. We're going to have a constant one, a piecewise constant one, and a continuous one, and they're all going to have similar forms to each other. So first, if all the values are constant, the angle of twist is the torque times the length over a constant g times the polar moment of inertia. Where g is equal to E over 2 times the quantity 1 plus nu. Where have you seen that before? That looks familiar, right? That's right. It's the, what do you call it, the reciprocal of what you see in the compliance matrix. That's actually the term that appears in the stiffness matrix. So 1 over G is the term in the in the compliance matrix. And it gives the relationship between the shear stress and the shear strain. That's what G is. Okay, so if torque, length, G, and polar moment of inertia are all constant, you have this formula. If they're constant over finite intervals, then you get the sum formula. So the torque on the ith piece times the length of the ith piece divided by G on the ith piece times the polar moment of inertia on the ith piece. And then you can also give it as a fully continuous integral formula. So the integral from 0 to L of torque as a function of x. Did I put the length in there? Hope I didn't. No, there is no length in there in the integral formula. The length is given by the dx. When you integrate that dx, it gives you the length. And same thing here, that shouldn't be in here. So torque as a function of x, dx, divided by G as a function of x, polar moment of inertia as a function of x.
Is it a good idea to say, like the previous problem where we had, you know how the shape was two different cylinders kind of
Yeah.
connected together? If you want to just roughly estimate, can you do the continuous, not the twist part, but the other one? Is it okay if you're just going to use the continuous length? You know what I mean? Instead of just drawing two cylinders, but make a cone. Like
The polar moments of inertia are going to change. So
for the twist, for the elongation.
for the elongation, and just do it as a cone.
Yeah, to make it a rough estimation.
I would say just, I don't know. I guess I'm sure there probably is a cone where you could prove that it was the same, you know?
Error might be a bit big.
Yeah.
But
It sounds harder to me, you know, I would just break it up. It sounds harder to figure out a cone that, you know what I mean?
Shouldn't it take less steps though? Just to know.
I don't know. I'm sure you could prove how, like, what ends the cone would need to have to give you the same answer, and I would guess that it's a fact, you know, and you could always do it that way. But I don't know what the error would be based on what, you know, what sizes of the two endpoints. I don't know any of that stuff. So, this is this is a shear stress. And this is a shear strain. So what that G is the constant of proportionality between a shear stress and a shear strain. That's why it's a term in the it's a term in the stiffness matrix, and the reciprocal is in the compliance matrix. Okay. Let's do a quick example. So let's say that we have a bar cantilever with a length of 0.6 meters. And let's say we have a external torque of 700 Newton meters. And The G value is 80 times 10 to the 9th pascals, and the polar moment of inertia is 1.57 times 10 to the minus 8 meters to the 4th. What's the angle of twist? Yeah, so we have to know what the internal torque is. In this case, it's just going to be 700 the whole way, but if you want to calculate it, you do this to tell you that, isolate the whole thing to figure out that the reaction torque is equal to negative 700. And then you do your cut. Now that you know that this is 700 this way, to find your internal torque T. And that says that T is equal to positive 700 Newton meters. And then the angle of twist is 700 times 0.6 divided by 80 times 10 to the 9th. And the polar moment of inertia, 1.57 times 10 to the minus 8. And you get a value of 0.334 radians. So a radian is about 60 degrees, so that's 20 degrees. Yeah, that is a lot. It depends which math you're using. If you, it depends what you're trying to calculate. If you're trying to calculate something that depends on the fact that the axes of the coordinate system don't change very much, then that's a little big. But if all you're trying to figure out is the angle of twist, and that doesn't produce any stresses above what the material can handle, then there's no reason not to trust that value. Yeah, but it's long too, it's, so you can get a big angle of twist without a big amount of strain, So, all right, that's all I have to say. Goodbye.